talk about probability and how it plays into propagation in networks. The models that we've talked about so far, the SIR models and the K-threshold models, even the firefighter problem, all assumed that there's a 100% transmission rate to susceptible individuals. So if you were adjacent to the right number of people who were infected and you were susceptible, then you became infected. But in fact, there are almost no diseases that are this contagious. Whooping cough, which if you're in my face-to-face class, you'll hear my personal experience with, is one of the most contagious diseases out there. It has about a 90% transmission rate. HIV, on the other hand, has about a 2% transmission rate. So if you're susceptible and you have sex with someone who's infected, there's actually a pretty small chance that it gets transmitted each time. The contagion rate for information is hard to predict. So for diseases, we can get a good estimate of how contagious they are. But for information, we don't really have a good number like that. So we're just going to make some assumptions when we're talking about how susceptible people are to catching a particular information, disease, or virus if they're in contact with an affected individual. So here's an example. We have a small social network here where all of our nodes are just in a line. So A is connected to B, who's connected to C, who's connected to D. We're going to start off assuming that A is infected. And now we're going to start introducing some of the variables. As I mentioned before, this is going to be a pretty mathematical topic, so we have to introduce some of these variables. We're going to let P be our transmission rate, and it's P because that's the probability of being infected. So we'll say P equals 0.08, which means there's an 80% chance that A will pass the disease to a neighbor. In fact, that any infected node will pass the disease to a neighbor. So in this simple example, what's the chance that B becomes infected? Well, B is only adjacent to one infected node, which is A. The probability that A passes the disease is 80%. Thus, there's an 80% chance that B is infected. And that's it. So this example is pretty simple. So if we carry this on, if B gets infected by A, what's the chance that C gets infected by B? Since C isn't connected to A, there's no chance it can get infected there. So the only way that C can catch it is if it's from B. So, if we know that B was infected, the chance that C gets infected is 80%. That's if B was infected. But B wasn't necessarily infected by A. So, the probability that C gets infected by B is 80% if B's infected. But we want to know what's the overall chance that C gets infected. Well, there's a couple things that could happen. First, in the first case, A could have passed the disease to B. There's an 80% chance that happens. And then if B has the disease, there are two possibilities there. B could either pass it on to C or not. If A never passed the disease to B, there's only one possibility. B can't pass it to C because B's not infected. So there are three total possibilities. A never passes it to B, so B can't pass it to C. Or A has passed it to B, in which case B either passes it on to C or not. The only way that C becomes infected is if A passes it to B and B passes it to C. If we want to look at the probabilities, we have to multiply them together. First, what's the probability that A has passed it to B? That's an 80% chance, or 0.8. And from there, if B is infected, what's the chance that B passes it to C? Again, it's 80%. There's an 80% chance that any infected node will pass it to its neighbor. So we have 80% chance that A passed it to B, and then an 80% chance from there that B passed it to C. So we do 0.8 times 0.8, which gives us 0.64. So there's a 64% chance overall that C becomes infected. Now this is a little hard to get all the details of on a slideshow with a lecture like this, so I strongly encourage you to look at the book which works out all of these exact examples that I'm presenting to you here. So what we've been looking at so far is where nodes just have one neighbor who's infected. Now let's look at the case of multiple neighbors. Here we have another network with nodes A, B, and C. But here, A and B are connected to C, and they're both infected. If we still assume an 80% transmission rate, what's the chance that C gets infected? First, we need to think about whether we're in a one threshold or a two threshold model. So let's start with the 2 threshold, even though that's the last bullet on the slide, because that's actually easier. There's a few possibilities that can happen here. A can pass the disease, and B can pass the disease, so they both pass it. A can pass it, and B will not pass it. B can pass it, and A will not pass it, or neither can. So there's 4 total possibilities. In the case of a 2 threshold model, only one of those 4 possibilities ends up with C infected. That's if both nodes A and nodes B pass it on. So what's the chance that A passes it and B passes it? Well, there's an 80% chance that it will get passed from A and an 80% chance that it gets passed from B. So we just multiply those 2 options together, and there's a 64% chance that both nodes have passed the disease on to C, and thus C becomes infected. So that's pretty easy. If we move to the 1 threshold model, 3 of those 4 scenarios that I outlined can result in C becoming infected. A can pass it, but B doesn't pass it. B can pass it, but A doesn't pass it. Both of them can pass it. The 4th option is that neither one passes it, and in that case, C doesn't become infected. So in our 1 threshold model, we want to consider 3 possible scenarios. We've said there's a 64% chance that both nodes pass it, but we also have to compute the probability that A passes it and B doesn't, and the probability that B passes it and A doesn't. So, if we start off with the probability that A passes it but not B, there's an 80% chance that A passes it. What's the probability that B does not pass it? Well, we want to keep in mind that when we're talking about probabilities, there's a 100% chance that something happens. So there's a 100% chance that B has passed it or that B has not passed it. If there's an 80% chance that B passes the disease, the only other option is that B doesn't pass it. If it passes it 80% of the time, that means 20% of the time it doesn't. So there's a 20% chance that B does not pass the disease. So, if we're trying to compute if A passes it and B doesn't, we have an 80% chance that A passes it and a 20% chance that B doesn't. We multiply those together, and that gives us a 0.16 or 16% chance that C gets infected that way. We also use exactly the same math to compute the probability that B passes it but A doesn't. In that case, there's an 80% chance that B passes it, a 20% chance that A does not pass it, which gives us a 16% total chance that C has become infected this way. So now we have 3 possible ways for C to become infected. The 16% chance it gets it from A but not B, the 16% chance it gets it from B but not A, and the 64% chance that it gets it from both. So we just add those up. 16% plus 16% plus 64%, which gives us a 96% chance that C is infected in a 1 threshold model. Now, if we have a 96% chance that C is infected, that means there's a 4% chance that C is not infected. And it works out nicely if we consider this 4th possibility, that A does not pass it and B does not pass it. The probability of that happening is 20% chance that A does not pass it, 20% chance that B does not pass it, and if you multiply those together, you get 4%. That's the remaining 4%, which absolutely makes sense. There's a 100% chance that C is either infected or not. In a 1 threshold model, there's a 96% chance that it gets infected, which means there's a 4% chance that it doesn't, and it works out in our math that the probability of not getting infected is that remaining 4%. So I want us to work a little bit more deeply at looking at the way these probabilities spread out. So here's a closer look. We're going to change our p-value to 0.6, which means there's a 60% chance that the disease gets passed. So let's look at this tree. We're going to start off with node A, and then we're looking at 2 options from branching off from A. It either passes the disease, there's a 60% chance that happens, or it does not pass it. There's a 40% chance. Notice again that that 60% and 40% add up to 100%. There's a 100% chance that A passes it or doesn't pass it. On each of these branches, then we're going to look at node B. So if A has passed it, then B can either pass it or not. And if A doesn't pass it, B can either pass it or not. And then what we look at the bottom is the probability that C becomes infected. So if A passes the disease and B passes it, we have a 0.6 times 0.6 chance that C is infected, which is a 36% chance. If A passes it but B doesn't, we have a 60% times 40% chance, or a 0.24. Notice that I'm just multiplying the values on each edge in this tree. If A does not pass it, but B does, we have a 0.4 times 0.6, or 0.24 chance that C is infected. And in this last case, A does not pass it and B does not pass it. Then C ends up not infected, and the probability of that happening is 0.4 times 0.4, which is 0.16. If we add up all these numbers on the bottom, these are the only 4 possibilities that can happen, and they add up to 1, which means there's a 100% chance that at least one of those things is going to happen. For all the examples I've given you so far, you can write out a tree like this. And sometimes it'll be simpler. Sometimes you just have A passes the disease or not, and then B either ends up infected or not. You can also have much more complex trees than this, and we'll look at a couple of those examples. But if you draw them out like this, for each step, drawing out all the possibilities, all you have to do is multiply the values down the path in the tree you're looking at, and that gives you the probability of ending up at the situation at the end. Now let's work a more extensive example. We have nodes A and B connected to C, and then in addition we have node D, and both C and D are connected to E. A and B are going to start off infected, and we're going to assume a transmission rate of 0.6, just like in the previous slide. What's the chance that C is infected in a one-threshold model? Well, on the previous slide, if we add up all those probabilities where C would end up infected, we end up with an 84% chance that C is infected. We're also going to assume that we have a probability of 0.7 that D is infected. And that's just an assumption that we're making here. We could have more of a network hidden here that we're not looking at, and that could give us a different value for D. But for simplicity, we're going to assume the probability that D is infected is 0.7. We want to know what's the probability that E gets infected in a one-threshold model. So we have an 84% chance that C is infected, a 70% chance that D is infected, a 60% transmission rate. What's the likelihood that E becomes infected? We're going to work this for a one-threshold model, but note that the tree that we draw will also give us the value we need for a two-threshold model. So let's draw this tree out. This is a lot more complicated than the last one, and this is in the book, so you can always look there to see a higher resolution version. This is bigger because we have to add in now probabilities that nodes are infected or not infected. In the previous tree that we looked at, we knew that the nodes were infected and we were just looking at whether or not they passed the disease. But here, we're looking first if they're sick and then if they pass the disease. So if we start with C, there's an 84% chance that it's infected and a 16% chance that it's not infected. If it's not infected, then we have to look at D. D has a 70% chance of being infected or a 30% chance of being not infected. If C is not infected and D is not infected, then E ends up not being infected at the end. And we just multiply the 0.16 times the 0.3 to get 0.048. So there's a 4.8% chance that E does not become infected because neither C nor D are infected. If C is not infected but D is, then there's a chance that it passes the disease or not. And again, we just multiply the values on the edges down the path. We do 0.16 times 0.7 times 0.6, which says that E gets infected from D. And if we go the other path, C not infected, D infected, and D doesn't pass the disease, then E doesn't catch it because it can't get it from C since C's not infected, and D didn't pass it so it can't come from there. If C is infected, then we look at whether or not D's infected. If C is infected but D isn't, then C has to either pass the disease or not. If C does not pass the disease, E's not infected. If C does pass it, then it becomes infected. And to get these values at the bottom, again, we just multiply down the path. 0.84 times 0.3 times 0.4, or 0.84 times 0.3 times 0.6. If C is infected and D is infected, then we end up with a tree that's very similar to what we looked at a couple slides ago. Then we look at whether or not C passes the disease, and in each of those cases whether or not D passes the disease. And again, we just multiply down the path. 0.84 times 0.7 times 0.6 times 0.6 gives us 21.2% chance that E becomes infected this way. Now, in a one threshold model, we're going to add up all of these probabilities on the bottom where E becomes infected, and that'll give us the total probability that E becomes infected. If we want to look at this for a two threshold model, then we only have to look at part of the network. We know for a two threshold model that both C and D must be infected and they both have to pass the disease. So we can cut off this entire branch where C is not infected and this entire branch where D is not infected. So we only have to look at this subpart of the tree here. From there, the disease only gets passed if C passes it, which means we can cut off this branch, and if D passes it, which means we can cut off this branch. So the only chance that E becomes infected in a two threshold model is if C is infected and D is infected and C passes it and D passes it. So there's only a 21.2% chance that E becomes infected in a two threshold model, where the chance is much higher in a one threshold model. Now, we can see that this is starting to get pretty complicated. And so sometimes what we need is simulations. So let's look at this pretty simple network here. A and B are going to start as infected, and they can infect C or D because there's edges all the way around. So if one node, say C, is uninfected, in the next time step it could be infected by A or B again, but it could also be infected by D. So say A and B pass the disease to D in the first round, so now A, B, and D are all infected. In the second round, C could catch the disease from A, or from B, or from D. This starts to get pretty complicated, because drawing those trees out gets really strange when we have lots of ways that the disease can pass over and over again. And if we change to an SIS, or an SIR, or an SIRS model, all these calculations change. The way the disease propagates at each time step changes, and this just becomes too hard to calculate by hand, especially in big networks. Those are some pretty dramatic trees that we were drawing out, and if you were to do the math by hand, and that's illustrated in the book, there's a lot of probabilities to figure out there, and that's only for a few nodes. If you have a network with even 1,000 nodes, which is pretty small, figuring out those values for 1,000 nodes gets really, really hard. So simulations can help with that. In a simulation, you take a network and you set some nodes as infected and others as susceptible. And when there's a probability that a node passes a disease, you're going to make a decision. It either infects or not. So you don't compute the probability. You know, say there's a 60% chance that it infects. And so you decide, does node A infect node F, yes or no? You make that decision. And you repeat for as long as the simulation runs, making a decision every time there's a probability. And then you get some results. And you repeat this simulation over and over and over from the same starting conditions, making decisions that sometimes will go the other way. So if you have a 60% transmission rate, in 60% of the cases you'll make the decision that node A infects, say, node F. But in 40% of the cases you'll say, no, node A didn't infect node F. So if you do this simulation a lot of times and look at the average result, you end up with a reasonable expectation of what would happen in the network. So we're going to do some simulations as a group, and I'm going to post a link to a spreadsheet so you can see what this looks like. We're going to assume an SI model, which is the simplest thing. That's what we've been working at in all of our examples. We have a one threshold, so just one neighbor needs to be infected. We have a transmission rate of 0.7, and we're going to take rounds just like we talked about in the previous slideshow. We're going to assume a susceptible node can be infected at each time step or on each round. And what you're going to do to make a decision is use a random number generator to get a number between 0 and 100. And I've got a link here to random.org. If your number between 0 and 100 is less than 70, you're going to make a decision that the node was infected. If it's 70 or above, you're going to say it wasn't infected. So here's an example. We have this network again, and we're going to say nodes A and B are infected, and just for simplicity of working through this, we'll say there's a 50% chance that D is infected. First, we want to know, does C become infected? So we're going to generate a random number to see if the infection comes from A. So I'll generate a random number. It's 84. Since 84 is bigger than 70, we're going to say no, the infection doesn't come from A. Now I'm going to generate a random number to see if the infection comes from B. This random number is 16. Since 16 is less than 70, we'll say yes, B does infect C. So C is infected. Now there's a 50% chance that D is infected. So first we need to decide if D is actually infected or not. We have to make decisions for everything. So we can just flip a coin. We'll say if it's heads, D is infected. If it's tails, D isn't. So we flip a coin. It comes up heads, so D is infected. So now we've made a decision. D is definitely infected. Now we want to know, does E become infected? Well, E could catch it from D or from C. C is infected in the example that we're working through. It caught it from D. So now we have to generate a random number to see if C will infect E. So we generate a random number, and it's 61. Since that's less than 70, E becomes infected. We don't even need to bother generating a random number for D now because we know E's infected. And so we'll just repeat this process over and over again until we see who ends up infected in the network. So now you're going to try this. Here's the network that you're starting with. D will definitely start off infected, and there's going to be an 80% chance that H is infected. That means you need to go to that random number generator, generate a number between 0 and 100. If it's less than 80, H is infected. If it's 80 or higher, H is not infected. That gives you your initial conditions. Then we are assuming we have a one threshold model, a 70% infection rate. And so you're going to go through the time steps. For each neighbor of D, which is B, C, and E, there's a 70% chance they get infected. So you'll generate a random number for each one to see if the disease gets passed. And the same for the neighbors of H and G. Now note that if node D infects C, you don't need to bother seeing if H infects it because it's already infected. But if D did not infect C, then you do need to generate another number to see if H infects it or not. So you're going to go through this, and I'll have you do 3 rounds. So first you'll check all the neighbors of D, and if H is infected, all the neighbors of H. That'll be round 1. Round 2 will be to check all of the neighbors of those infected nodes, and then round 3 will be to check all the neighbors of those infected nodes. When you're done, I want you to write down how many nodes in your network ended up being infected at the end. I'm going to put a link to a spreadsheet on the website, and I want you to enter your name and the values for your stimulation. And what you'll see is that there's a column at the top that'll show the average for the infection rates in the class, and we'll see which nodes have a higher likelihood of being infected in this network. Again, this is a pretty complicated topic that we've gone through in this lecture, so I highly encourage you to go through the book and look through the examples which are worked there in more detail. But hopefully this has given you an idea of what goes on when we're really modeling complex propagation of effects through networks, and how we use both statistics and simulation to achieve interesting results.